Okay, welcome everyone. This is New England Dynamics and Number Theory Seminar, November 2020. And we're very happy to have Alon Agin from Tel Aviv, who will tell us about constructing best approximation vectors. Your floor is yours.
Okay, so thank you. Hello, everyone. Firstly, I'd like to thank Dimitri and the organizers for inviting me. And secondly, as I guess all of you or some of you know, these are a bit of difficult times in the Middle East. And preparing the talk wasn't that easy. I mean, doing math in these days is not that easy. And I've decided to share with you a link honoring the following members of the Tel Aviv University community. At the end of the talk, I'll maybe copy it and I'll send it in the chat, and if some of you would like to take a look at it. And I'll start the talk with a hope for better days in our area.
Yes, we'll of course all agree, and thank you for saying this.
And thank you for the nice words. So the title of the talk is Constructing Best Approximation Vectors. The subtitle, which is maybe a bit more accurate, is an alternative introduction to the Diophantine approximation with recent results. And the idea of the talk is for us to discuss some very classical results in the Diophantine approximation that I guess all of you or some of you are very familiar with, but in a bit of a different language or a bit of a different perspective, and then to discuss some recent results. The talk, I believe, would be no longer than 45 minutes. I hope it to be an easy and slow talk. And if some of you have questions throughout the talk, please feel free to just stop me at any time and ask questions. So again, I'll start slow. I'm sure that all of you are familiar with best approximations, but I want to define it to do it in the proper way. So we have a vector on Rd, and we have an arbitrary norm, and we define the best approximation sequence of that vector v with respect to the norm that we work with to be a sequence of the form Qn and Pn, where Qn is a natural number and Pn is an integer vector, which satisfies the following inductive procedure. We start with Q0 being 1, and after we've chosen the first n-1 pairs, we choose Qn to be the next natural number that allow us to get a better rational approximation than the previous rational approximation of V that we have, meaning that there exists a P that enables us to get this inequality. And then we choose Pn to be a minimizer of this quantity, meaning that for all other P's, the norm of Qnv minus Pn is less or equal than the norm of Qnv minus P. And for those of you who are not that familiar with best approximations, and if you haven't realized the procedure, the idea informally is the sequence is just the best sequence which satisfies that the Qn's, we usually refer them as the denominators, inform an increasing sequence, and they enable us to get a decreasing sequence of rational approximations of V. Now, usually in the Diophantine approximation, you start with the Dirichlet theorem, and then you go to the best approximation sequence. For rhetorical reason, I do it the opposite. So now I'm going to state a theorem which I'm going to call a generalized Dirichlet theorem. This is not a popular theorem. It's suited for this kind of talk. So I'm going to state it as 1 and 2. The first thing is that the sequence of best approximations of a vector V is an infinite sequence if and only if the vector is an irrational vector. And furthermore, not only that this rational approximation form a decreasing sequence, but they always go to 0, assuming that V is irrational. If V is a rational vector, then this procedure just stops at some point with a rational approximation that is equal to 0. So now that we know this, you have a fundamental question of who wins in this race, right? The Qn's, they go to infinity. The rational approximations, they go to 0. And Dirichlet theorem, in the way that I'm going to state it now, gives you a way to quantify these sizes. So it states the following. It states that there exists a constant. I'm going to call this constant throughout this talk gamma. which is dependent on the norm that we work with, such that for all v and for all sufficiently large n, we have this inequality. If we take qn plus 1 and we raise it to the power of 1 over d, and we multiply it by the nth rational approximation, this is always bounded by a uniform bound that holds for all v's. I'm going to add in here another trivial inequality where I only replace the qn plus 1 in here with qn, just to keep in mind the motivation of who wins the race between these two guys. And two comments is, firstly, I assume this gamma to be minimal with this property. This is a small statement at itself, but it is true that indeed this is a minimal and not an infimal number. And once I look at gamma to be this number, I just want to say that this is an important number. Up to some constant, this is the Hermite constant or the packing density of RD, which is an important constant that for an arbitrary norm and arbitrary dimension, we do not know what is this constant. We only know that this constant exists. So we look at this equation, and this leads, in my opinion, to two very natural definitions. So if Qn is the best approximation sequence of V, we define the nth short displacement vector of V to be just the vector itself, which satisfies this inequality, and the nth long displacement vector of V to be this vector itself, which satisfies the inequality. And for convenience, I'm going to denote the short displacement vectors as alpha n's, and I'm going to denote the long displacement vectors as beta n's. And from now on throughout the talk, you should remember that Qn, Pn, alpha n, beta n, these are all functions of a vector v, but I'm omitting the v from the symbols from now on and just keep it in mind. So I draw a very basic picture just to make sure that everybody understands. So let's say that we're in dimension 2, and we have a ball around the origin with radius of this magical constant gamma. Let's say that the norm that we work with, this is how the unit ball of it looks like, and it's scaled to gamma. And now we have a vector which is somewhere in the plane. Let's assume that it is irrational, so the theorem is interesting. And the theorem tells you that starting from some point, you have two infinite sequences, the beta n's and the alpha n's, which are always inside this shape. They always have the same direction. They can be close, like in here, and they can be far away, like in here. But beside of it, a priori, you do not know anything beside of it. And throughout the talk, I want to focus on three aspects of these sequences. I want to focus on the length and the direction of the displacement vectors, and I want to focus on the congruous class of the D+1 tuple Q and Pn. Now it's written in here, basically this is a talk about the beta n's, about the long displacement vectors, but I denoted also I defined also the alpha n's because I'm going to refer to them in a few places. But generally this is a talk about the beta n's. Are there any questions at this point? Great. So I'll start with the typical case. So in 1917, Davenport and Schmidt showed that if we take the maximum norm, then for almost every V, the limb sup of the lengths of beta n is equal to this magical constant gamma, which in this case is the number 1. And since then, people try to generalize this result. It was a procedure where people had some results, and this ended 3 years ago by work of Dimitri and Anurag Rao, which showed that this is also true for the general case, meaning that for every norm that we take, and almost every V, the limb sup of the lengths of the long displacement vectors is always this magical constant gamma. In terms of a bit of history, this proof was a proof, a number theoretical proof, a combinatorial proof, and this proof is a dynamical proof.
Well, let me just comment that we didn't really do much in terms of the new stuff, because dynamical proof was around since the work of Dani, so it was clear that this dynamical proof also produces this new result. So we're basically recording some ideas that existed before.
Another way a way to describe this fact in a more popular language is that almost all vectors in RD are not Dirichlet improvable, meaning that we cannot improve the Dirichlet theorem that I stated before. In 2001, Chevalier showed a similar result regarding the lim inf, where he showed that for almost every v, the lim inf of the lengths of the beta n is equal to 0. Now it's a time to say that we say that a vector v is badly approximable if the lim inf of the short displacement vectors is strictly greater than 0. This is not the popular definition of badly approximable vectors, but again, I use this kind of language in this talk. So particularly, Chevalier showed that almost every v are not badly approximable, where this is, he proved it in a much stronger sense. As far as I know, the first proof to this was also by the works of Davenport and Schmidt in 1970. Regarding direction, so this is regarding the length. Regarding direction, in 1951, Roger showed that if we take the maximum norm, then two consecutive displacement vector, it can be either the beta ends or the alpha ends, they cannot lie in the same quadrant. And again, in a similar process, there was a thought for some time whether or not this fact can be generalized to arbitrary dimension and arbitrary norm. But in 2000, Nicolai showed that this is not true for the general case, where he showed an explicit counterexample in dimension 2, where all the displacement vectors are inside the same quadrant. In 1983, Bosma Yeager, and I'm sorry, but I don't know how to pronounce the third name, if someone wants to help me with it. But these authors, they showed that for dimension 1, there exist probability measures, mu1 and mu2, such that for Lebesgue almost every v, the sequence of short displacement numbers equidistributes with respect to mu1, and the sequence of long displacement numbers equidistributes with respect to mu2, where these measures are nice in some sense, they're continuous with respect to Lebesgue. And a year ago, Barak and Uri Shapira, Barak Weiss and Uri Shapira, they generalized this result to arbitrary dimension and arbitrary norm for the alpha ends, for the short displacement vectors. I didn't want to write it down, but Barak is suggesting that the method of generalizing this to this should also work for the beta ends, and the reason why they did it for the alpha ends was because they had more interest in it. Regarding congruence class, so also in the work by Uri and Barak a year ago, they showed that if you fix z any natural number, then for Lebesgue almost every v, the sequence of best approximation of v are distributed uniformly, I'm not being too precise in here, between residues modulo z, which are valid. And this is a result which is not dependent on the norm that you work with. So maybe, and again, this is a generalization of a work from 82 by Morekel. So maybe I'll go back to the picture, and now let's try to understand what's the typical case. The typical case tells us that we have the beta ends have a subsequence that converges to the boundary of this shape with radius gamma. They also have a subsequence such that the beta ends converge to the origin, hence also the alpha ends. In terms of congruence class, you should not expect to have any interesting behaviors. Things should be quite random. And we have an equidistribution theorem with a measure which is nice, telling us that thing in general should be quite arbitrary. We have an arbitrary behavior for almost every V. Okay, so this is regarding the typical case. I'll now go to the non-typical case. In the non-typical case, I'm going to discuss only length. So let's just remember what I've just said. For almost every V, the limb sup of the lenses of beta n is gamma. So we have a question, what values between 0 and gamma can be obtained as a limb sup of a long displacement vector for some V? So this question refers to the object which was introduced about 10 years ago called the Dirichlet spectrum of RD with respect to a norm. The usual definition where this object appears is taking all of the values that can be attained as limb sup of this function, where you take t to be in the power of 1 over d, and then you look at, you multiply it by the rational approximation you can get to v via q's which are bounded by t. But this is in fact just taking all of the values that can be attained as a limb sup of the lenses of the long displacement vectors where v ranges in RD. So clearly, an immediate observation is that the Dirichlet spectrum is a subset of the segment between 0 and gamma. For d equals 1, by the works of many people, especially in continued diffection, we know that the Dirichlet spectrum has a complicated structure. In particular, it is not the segment between 0 and 1, where 1 plays the role of gamma for this case. And this is known not by works of the Dirichlet spectrum, but many different work that if you combine them together, you get something very, very messy. And the surprising fact that was observed 10 years ago by Akonjanov and Shotskov, they showed that if we're in dimension 2 and if we're taking the Euclidean norm, then the Dirichlet spectrum with respect to this dimension and norm reaches its full potential, meaning you can get the whole segment between 0 and this magical constant gamma, which in this case is this number. And I wasn't around to know about it, but as far as I understand, this was a very, very surprising result, again, because it's very not intuitive because of what happens in dimension 1. A year ago, Schleichitz showed that if we're in dimension greater than 2, and if we take the maximum norm, then again, we have the same phenomenon. The Dirichlet spectrum reaches its full potential, where in this case, the gamma is equal to 1. Schleichitz also showed that if we take a norm which he called an expanding norm, I'll define it in a second, then there exists a constant m, less or equal than gamma, such that the Dirichlet spectrum contains the segment between 0 and m. Where we say that the norm is expanding if for all v, the norm of v is less or equal than the norm of the orthogonal projection for all of the coordinate axes. Okay? And in these days, I think you can say that we have a conjecture that everybody around thinks it's true, which is that for all d greater than 2 and every norm on RD, the Dirichlet spectrum would reach its full potential, which is between 0 and gamma. I know about some people who are working on this, including myself. And I think it would be interesting not only if someone will be able to prove it, but to also understand maybe philosophically, what's the big difference between dimension 1 and the dimension which are greater than 2. So I want to discuss in shortly some refinements of the Dirichlet spectrum. So I'll define the badly approximable Dirichlet spectrum of RD with respect to a norm to be again all values that can be attained with the same function that I stated before, but now we do not let V to range in all RD, but we only look at vectors which are badly approximable, meaning that we're looking at all values that can be attained as a limb sup of lengths of the beta ends with the requirement that the lim-inf of the short displacement vector needs to be a number which is strictly greater than 0. And a year ago, also, a very nice result regarding this object was obtained by Akonjanov and Nikolai, where they showed that if we're in dimension 2, again, and the Euclidean norm, then the badly approximable Dirichlet spectrum is dense inside the Dirichlet spectrum. So a question regarding non-typical case and length is whether or not can we have better control on the lengths of the beta ends rather than controlling only their lim sup. So I'll introduce a definition. We say that a vector is Dirichlet converging with respect to some norm if the limit of the lengths of beta ends exists. And we continue from this and we define the limiting Dirichlet spectrum of RD to be all of the values that can be attained as such a limit. And in the work of Akonjanov and Shatskov in 2013, they actually proved something which is much stronger than what I've stated before and what people sometimes say that they proved. They not only proved that the spectrum reaches its full potential, but they show the followings. They show that if we have dimension 2 and the Euclidean norm, and we take IN to be any sequence of closed non-degenerate intervals that all lives inside the set, the segment between 0 and the magical constant gamma, then there exists continuum many vectors such that for each one of them, you can have full control of the lengths of beta ends. The length is inside IN, meaning that at each step, you can control the length of beta n up to an error term, which is as small as you want. Okay, so particularly they showed that the limiting Dirichlet spectrum reaches its full potential, and in this case, it is actually equal to the Dirichlet spectrum. And I'll say that as far as I know, this is the only result regarding this object. More than this, as far as I know, this is the only proof that the set of Dirichlet convergent vectors is even an infinite set. And in my opinion, this is an interesting set, an interesting object, which is completely not being investigated. You can think what happens in higher dimension. You can think what is it's outside of dimension. And this is the only thing that we know about it. So the next thing that I'm going to do is I'm going to discuss my work. My work is my master's thesis. I think this is a good time for questions if someone has something to ask. Okay, great. So now the theorem that I'm going to state, the introduction of it will be a bit more heavy. There will be a picture afterwards that will make it easier. So we start with an arbitrary norm on R2. And I want to say, I should say, I'll go back. My work is a generalization of the work of Akonjanov and Shatskov that generalizes their work in some aspects. So we have an arbitrary norm on R2. Then there exists an explicit constant. Explicit, I mean that I can calculate it, but I don't want to get into it right now, such that the following is hold. So firstly, we let theta to be an angle between 0 and 2 pi. We let delta to be any number greater than 0. And we define omega to be the sector, the part of the plane of all vectors that has angles within this range. We let IN to be a sequence of closed non-degenerate intervals that each one of them is a subsegment of the segment between 0 and m. We fix Z to be a natural number, and we let Kn to be a sequence of residues mod Z that satisfies this condition. It will become understood in 2 minutes why does this condition appears. And the theory tells you that there exist continuum many vectors in R2 with best approximations such that the following holds. Firstly, length. So the length of beta n again, we have full control of it at each step, beside of an error term, which is as small as you want within the segment between 0 and m. Secondly, direction, the beta ends are inside omega. And in a similar way to what we've talked about, the result by Rogers, two consecutive displacement vectors, they always lie in opposite quadrants. They cannot be in the same quadrant. And C is arithmetical control. The sequence of denominator is always equal to Kn mod Z for all n. Furthermore, this vector is not badly approximable, meaning that this kind of a result does not help us with the badly approximable Dirichlet spectrum. Every three consecutive best approximations, they form a basis of Z3. This is not a trivial thing to do. This is not what's supposed to be. And in the case that the norm that we work with is a norm that looks like this, meaning that the unit ball of it is an ellipsoid, which is not twisted, then M is best possible. M is equal to gamma. Now, I want to say in short something about this condition. So if this condition follows from this condition, okay? If every three form a basis of the lattice Z3, then you cannot have a stronger or a more general condition on the arithmetical control than this one. And I don't know if it's obvious right out, but if you think about it for a few minutes, it's obvious. So I'll go back to exemplifying the result with pictures. We have a ball around the origin with radius gamma. And inside of it, you have a ball of radius m. And the theory tells you that you pick a sector omega is just an angle that can be as thin as you like. And now you can put the displacement vectors anywhere that you want inside this ball of radius m and inside this sector omega with an error term which is as small as you want and with this kind of conditions. So I'll go over to some corollaries. The first corollary is take an arbitrary norm on R2, then there exists a constant m such that the Dirichlet spectrum and the limiting Dirichlet spectrum contains the segment between 0 and m. Furthermore, if we have a norm which looks like this, for example, Euclidean norm, then this reaches the full potential. You get everything. The second corollary is a corollary for the space of lattices. I'm gonna talk about it quite quickly. Those of you who are familiar with these symbols will understand it immediately. Those of you who are not, I guess it will be a bit more difficult, but I don't want to waste too much time on it. So we take an arbitrary norm on R2 and we denote by X3 the space of unimodular lattices in R3. Then for all R inside the segment between 0 and m, m is the same m as in the theorem. There exist continuum many lattices such that R is the minimum over all epsilons, such that the trajectory GT lambda leaves this compact set for T large enough. I'll specify the definitions. So the norm that appears in here is the norm on R3 that we do by this norm, where we're taking the max of the norm, the absolute value of X and the norm of Y. The set K epsilon with respect to this norm is all of the lattices in X3 such that all of their non-zero vectors are greater or equal than epsilon. And GT is just the diagonal flow of e to the power t, e to the power t, and e to the power e minus t. So I'll draw the picture in the space of lattices. We have the space of lattices in here. We have the compact set KR. And the theory tells you that you can find the trajectory you can find a lattice such that this trajectory leaves this compact set at some point and never come back to be inside of it, but it comes infinitely close to the boundary of it infinitely many times. Okay? So the last thing that I want to do is I want to talk for 5 to 10 minutes about the proof. I'll be quite general. I'll try to explain the motivation and the philosophical ideas behind it, but I don't want to get into too technical. The paper has a lot of calculation, and it can be a bit difficult to read. So I want to stress out the ideas. So firstly, for a vector Q and Pn, we denote for convenience Vn to be the two-dimensional vector of Pn divided by Qn. And the idea of the proof is a proof by induction. And we're looking for a sequence Q and Pn such that the following is solved. So firstly, we want that the Vn's will be a Cauchy sequence, meaning that we will have a limiting vector. The second thing is we want that this limiting vector, that this Q and Pn would be the best approximation of this limiting vector, something which is not obvious at all. And in order to do so, again, I don't want to get too technical in all of the equation, but the idea is that we take the definition of best approximation that we started with, and in this kind of inductive procedure, you do not have a V in here. You do not have a vector that these guys could be the best approximation of it. So what you do is at each step, you have a finite amount of requirements where the Vn is taking the place of V. If this applies to all n greater than 1 and for all j within this range, then this sequence must be the best approximation sequence of V. In here, what's written, if you think about it, if now you'll take n to infinity, then what you'll get in here, because of continuity, what you'll get in here is just the norm of the vector beta j. So if we require that at each step, this will be inside the interior of the segment ij, we will get the property A holds. Similarly, we'll do the same with the direction. And similarly, we'll do the same with the arithmetical control. Now, I'm assuming that understanding why this kind of an inductive procedure yields the result is not possible so quickly. But the idea is that if you want to prove the theory, or a theory as such as I've stated before, and you want to do it by induction, then the understanding that the induction procedure should look like this is fairly easy. It is not difficult. The difficulty is if you assume that everything holds up to the n-1 step, how do you construct the next step? And this is the very nice and crucial observation that was made by Akhondjanov and Shatskov 10 years ago, where they understood that you should try and pay attention to property number 2. Okay, so I've copied it in here. And again, I'm going to be not precise at all. I just want to get the idea. So if we assume by induction that we have Q0, P0 up to Qn minus 1, Pn minus 1, where everything holds, we define B to be all of the xy's in R3, where now we replace, at the moment we do not have Vn, and instead of looking at rational vectors, right, a Vn is a rational vector, we look at it as a real vector. Okay, we replace in some sense this argument for the n-1 step with a real vector, and I'm not specifying for the moment what exactly should happen in here, but it's not that complicated. And i.e., if a point is inside B, and if we are able to explain why such a point is also an integer vector, then by setting Q and Pn to be this point, we have a very good candidate to satisfy property number 2. And the surprising fact is that this set B has very nice analytical properties. You have very nice calculus that you can do on it. You have very nice arguments of number theory you can do about it. And although this set looks like a set that you almost don't know anything about it, Akonzanov and Shatskov, they noticed that you can investigate it fairly good. So after analyzing the set, we show that there exists a vector Q and Pn which satisfy 1 up to 5 from above. And that's it, if you have any questions. I maybe can go to this slide, although
Can I ask a question? We should have progressed before about the typical case.
yes.
So for the typical case, there's the set of lengths are equidistributed. I might have missed it. Are the direction also equidistributed, or we know that they are not?
I don't. Can you speak a bit louder?
For the typical case, you mentioned the result that the set of length is equidistributed with respect to some measure. And the question is, are the direction also distributed in a certain way, or we don't know, or we know that?
So the direction is a norm-dependent result. If you take the maximum norm, then you know that 2 consecutive displacement vectors cannot be in the same quadrant, but you have a very strong equidistribution theorem from a year ago. And this equidistribution theorem, I haven't said anything about equidistribution with respect to what measure, but this measure is a nice measure. And in some sense, you have an arbitrary behavior. Beside that, for some norms, for example, the maximum norm, you can have something like 2 consecutive ones cannot be in the same quadrant. But beside of it, you should expect any direction that you want.
So the set of all points of all vectors will be dense inside the ball for this gamma in general.
Yes. Yes.
Okay, so maybe I should repeat Alon's question as to whether or not other people have questions. So my question, I guess, would be to what extent. I mean, it's basically. I mean, like you had this picture showing this compact set and trajectories which left and then touching this compact set. This space of lattices. So first of all, this what you are doing is specific to X3. If you add the dimension, move the dimension up, it's not clear what is happening. And also, I mean, so what we have is a dynamical system and a family of increasing or decreasing compact sets, and you want to construct trajectory with this very prescribed properties. So I'm just curious to what extent this can be turned into a dynamical proof, just looking at the trajectories of lattices. But maybe it's a rhetorical question.
I didn't understand the question. I thought you were asking the audience, but now I understand you're asking me.
Well, if the audience have some feedback, I'll be happy to hear them too. But what do you think?
If I understand you correctly, then
So,
in terms of dynamics, I don't know how to say. I don't know how to say anything. I mean, the corollary is very easy. It's very straightforward. And in fact, it shows that controlling the lengths of the beta ends is in some sense similar as controlling the lengths of the shortest vectors of this trajectory. So you can have various corollaries, you can have also different corollaries. But the idea is that once you can control the beta ends at each step, you can write lattices with very prescribed geometry. I know from Barak that this kind of a corollary is interesting.
Mm-hmm.
And for other dimensions and other norms, then if you know things about the Dirichlet spectrum, then I think this everything looks the same, beside the fact that in here you need to change the minimum to an infimum. You need to have a limit of the beta ends in order to have a minimum in here.
Mm-hmm.
And beside of it, I don't have anything smart to say, I think.
So I'm also curious about the result that you mentioned in the beginning, that you have liminf equal to 0 almost surely.
Mm-hmm. Liminf of the beta ends.
Liminf of the beta, yes.
Of Chevalier.
Of Chevalier 2001. So I'm trying to make sense of it dynamically as you're talking. So it's about orbits which are unbounded in a certain way. I mean, so it's not just unbounded orbits. It's unbounded with some extra property. Can you restate it using this family of KRs or K epsilons?
I'm assuming that it means that almost these trajectories, you have that if you have if you choose a trajectory of this form, then it will go all over in the space. I mean, it will go to anywhere. It will go and come back. It will go and come back, but it won't be badly approximable. And if I don't know how the beta ends play a role in it.
So if you have a trajectory which is equidistributed in the space of lattices, then this liminf is 0.
Yes, but I don't know. I don't know in terms of the picture. What does it mean?
I'm confused. How do you know this?
The liminf of what? Excuse me. I thought the liminf of the shortest vector.
Of beta ends, yes. Okay, maybe we can talk later. Just something that I'm trying to understand from a dynamical perspective.
Mm-hmm.
And so far I'm not. Maybe the audience can help me. Alpha ends. If alpha ends, if liminf of alpha ends, liminf of alpha ends is 0 if and only if trajectory is unbounded, right?
Mm-hmm.
But now you have a stronger property. It's not just unbounded, but also something else happens.
Mm-hmm. Yes, you're right. But I don't know. I don't know what's the heuristic of it.
Okay, maybe I should look at Chevalier's paper. All right. Any other questions, comments? Okay, then if not, at least we should have a virtual round of applause to Alon for for this
Thank you.
wonderful talk, and of course we all hope for peace in the long term, in the short term, also in the long term. Thank you very much.
Thank you.
You wanted to mention this web page again?
Yes, I do. So let me. I'll send it in the Zoom, in the chat.
Yes, thank you.
I've actually looked for a similar page that gathers all the academy people from academy in the Middle East that are no longer with us since the October 7th, but I haven't found anything. I only found of Tel Aviv University, so this is what I've put.
Yeah, anyway, it is very sad, and I hope this ordeal will end soon.
Yes.
Anyway, if there are no questions, let me thank Alon again.
Thank you, Dimitri.
Thanks for coming, and look forward to future talks.